Okay, and this is really kind of, well, it's different expansions, okay? So the objective, so here, so we want to understand orthogonal functions. Functions. An eigenfunction expansion. Okay, so this is going to be section 12.1 of ZIL. Okay, so there's some other things before I get into that. Okay, so I'm going to have office hours today. Office hours. 207B after class. Oh, and Lord House 207B. Oh no. Okay, and this is in Lord House. So this is after class. I wanted you guys to try these. So try the boundary value problems. So maybe I already told you guys to do this. So try the boundary value ODEs in section. This is section 3.9. So have any of you guys tried to do these? So so on the website, I'm going to update the web page, but the web page had these flipped. So I'm going to after this, I'm going to go to my office. I'm going to update the web page for next week, so you guys can see what quizzes and what problems are coming up. And then one of you emailed me. Who emailed me? Yeah, about whether or not we were going to do this one. But if you guys should try the problems, and then I'm going to ask you on Monday how it went. If it went okay, then we'll have the quiz on Wednesday, right? If not, then I'll review some things, okay? Because there's some weirder boundary conditions type problems that we'll have to deal with later that involve derivatives instead, okay? So see if you can do those problems, and then okay. The other thing is that I'm gonna send out a survey, and then if I get a good response rate, so if everyone responds. I'll give you, everyone gets a free half a quiz. Okay, so I'm just going to give everyone half a quiz score if everyone in the class responds. Okay, and then the other thing is I'm going to update the web page. Later today. I'm going to try and do it at the end of the week from now on. Okay. All right. Do you guys have any other questions about anything, administrative or otherwise? Okay. If not, then we'll get into back into talking about these things. Okay. So I've kind of repeated what we've been talking about. So again, so the motivation, right, was that. If we can write our initial, our initial data. So these were the initial conditions. So the functions that you had, so you had the two initial conditions. You had for the vibrating string problem. So if we can write our initial data in the vibrating string problem, as an expansion of eigenfunctions, like an. So this is for this very particular problem that we've been talking about. So you guys, I don't want to write down everything again because it's long. It takes a long time to write down. Right? Then for these TNTs, and we can solve the full problem. Okay, and so I told you that there was like a magic formula for this that Euler gave. Okay, so I'm going to write down the formula. Okay, and then I'm going to go and try and explain where this comes from. Okay, so here's the formula. So here's the formula. Okay. So I'll do it for f, right? For f of x. So here, so f of x, okay, so f of x is equal to the sum, n is equal to 1 up to infinity. And now I'm going to have to say what these things are. So, well, I'll have to explain what these are. These are going to be inner products. Okay? And so this thing, and so let's say for two functions, so 0 to 1. Okay, so here's, oh, so f and h. Okay, for arbitrary functions. Okay, it could be like this. Okay, so here, this is what we have. Okay, so this is the formula that you have, right? So this is this is what's called an eigenfunction expansion, and it gives an infinite series expression for this thing. In particular, these guys here. So in particular, the ANs are given by this thing. And I'll have to explain what these symbols mean. Well, I guess I sort of explained what they mean. They're this. Okay? So we can actually get what the coefficients are. One thing is that this equality is a little dubious. Okay? So maybe we can put that in quotes or something. Okay? So it's not going to be exactly equal all the time, right? But I'll say a little bit more about that in a bit. All right. Okay. So all right. So this is what this is the formula that I want to explain. Oh, sorry, G. Yeah, excuse me, G. Okay. So let me do. Can I do H1 and or I don't know. Maybe I messed up your thing. Yeah, this is supposed to be. I didn't want to use the same letters. H1, H2. Let's do that. H1, H2. Sorry. So these are, you just take two functions on this interval, and then you can take their inner product this way. Okay? And let me say a little bit about inner products and orthogonality and this sort of thing. Okay? So let me start in on inner products, and this will be like a little bit of a review, and then I'm going to try and make this formula look familiar to you. All right. So recall, so that V and W in R3, so these are just two vectors, are orthogonal. All right, provided that V dotted with W is equal to 0. Okay, so that's what it means for two vectors to be orthogonal. Okay, so here, if V is equal to A1, A2, A3, and W is equal to W1, W2, or sorry, let's say B1, B2, B3, I want to remind you guys that V dotted with W is A1, B1 plus A2, B2 plus A3, B3. All right? So the reason I'm doing this is I'm giving you an example, okay, so of things, and then we're going to generalize what's going on here. And let me show you the picture again of what it means for two vectors to be orthogonal. It means that they're perpendicular, right? So the picture, well, let me draw this dot product picture in general. So if here's W and here's V, right? We have this angle theta like this, okay? We have this formula for V dotted with W, and it's the absolute value of V, or so the norm of V, the norm of W, cosine of theta, okay? And so here, right, so this is that's from Calc 3. And so when they're 90 degrees, right, theta is equal to pi over 2, right, and then that thing becomes 0, okay? So that's when, that tells you that these two things are in the exact opposite direction. So these are orthogonal vectors. And so I told these guys before, the people who were in my Calc 3 class, that this thing measures how much V and W are going in the same direction. So if it's positive, right, they're pretty much going in the same direction. So, and so we can recall, let's also recall that, this thing, this norm squared, this by definition is VV. Okay, so oh, I didn't say this yet, okay? So this is V dotted with V. Okay, and let me introduce a new notation that we'll use, okay? So this is used a lot, very often. And this is one of the reasons why I don't like the way the calculus book writes vectors. But this is a very common notation for inner products here, okay? So this is just like a angle brackets with this, and this means a dot product, okay? So this is a new symbol for inner products. Well, it's kind of a general inner product. Okay, well, let me just say, this is an example of an inner product, okay? All right. Okay, so let me say one more thing. And I want you guys to think about this formula in regards to the formula that I'm going to write. Okay, so here's something that we can do. Okay, so here's kind of a thing that we can do. So if V1, V2, and V3 are in orthogonal basis of this vector space R3, then what we can do is we can decompose any vector into a sum. Well, we can always decompose into a basis, but we can decompose any, let's say, W in R3 as with the following formula. Okay? So W can be written like a combination of V1, V2, and V3. And the combination is as follows. So you take the inner product of W with V1 divided by, well, the norm of V1, like this, times V1, plus the inner product of W with V2, times the norm, oh, sorry, this is, okay, let me explain what this thing here is, V1. Okay. Let me write out the formula, and then we'll, here, So I'm just going to copy, do it with v3. Okay. Like so. Okay? So, okay, I've written this in a certain way. So this is the amount of v or amount of w that's going in the direction of this unit vector. Okay, so this is the unit vector in the direction of v. Okay, and this thing is really the inner product of w with the unit vector of v1, right? And so what you're really doing is you're taking w and you're breaking it into, this is the amount of w that goes in the direction of v1 times the unit vector in the direction of v1. Right? This is the magnitude of w going in the direction of v2 times the magnitude of v2. And this is the magnitude of w going in the direction of v3. Oh, this is not right. This is v3 over the norm of v3. Okay? So this thing here, if we recall that from this thing here, so this is really just the sum, or we can write this as the following. W is equal to the sum from j is equal to 1 up to 3. Or let's say k is because of Owen, because he uses j's for the square root of -1. Okay, so w vk, right, over vk, right, times vk. Huh? Does that look familiar to that formula over there? Right? So this formula about decomposing into constituent parts is the same thing as this formula here. Or it's a version of this formula here. And what we're going to do is we replace this inner product, the usual dot product. Where is it? The dot product over here. This dot product, where this is the formula for the dot product. We're going to replace this dot product with this sort of product-looking thing, and we're going to replace these basis vectors with other functions. Okay, and these functions are going to be these things. So these things are like different directions in an infinite dimensional space. Is one way to think about it. Okay, so these will be orthogonal vectors. Okay. Okay, so, all right. All right, so let me make some remarks here. So questions on this thing? You guys want, maybe I can break down one of these for you guys geometrically. Maybe this will be helpful. So just as a refresher from Calc 3. Okay, so let me draw the picture. Okay, so this thing here, so this thing here over times this vector. Okay, so this thing is the projection of W onto V1. Okay? This piece here is the unit vector in the direction of V1. And this thing here, well, this thing looks like, well, this is the magnitude of W in the direction of V1. All right, and now let me do the picture here. So here's W. Here's V. Okay, and then this thing here. Let's say, sorry, this is W. Sorry, V1. So let's do this. This is V1, and this is W. Excuse me. Okay? Okay, so this thing here, this is the unit vector. So it's just like this is length 1. And this thing here is, so this vector is v1 over the magnitude of v1. Okay, so this thing here has norm 1. All right, let's see if I can do this. So I guess this is supposed to be a projection onto this thing. So this length here, this is the magnitude that we were talking about there. And this is the norm of W, if this is theta, times cosine of theta. And the fact that this length here is this can be gotten from this formula here. Right? So that's what tells you this. Okay? So that's this length here. And so what we've done is we've taken, so this is equal to this thing. This is equal to W V1 over magnitude of V1. Okay? So you can plug that in, right? And you'll see what this is. Because look at this. You plug this in to here, and then the magnitudes of the V1s would cancel, and you'll just get the magnitude cosine theta. Okay? All right. So this is the picture. So we've really just made, so that this whole vector here, the projection is this vector. So this thing is the projection. Okay, so, all right. Okay, so okay, so let me just say the above discussion. So more generally, so if V is equal to Rn, we can define, this inner product of x with y to be x1, y1 plus x2, y2 plus dot, dot, dot plus xn, yn, where we had x being x1 through xn and y being y1, y2, dot, 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 yn, like so. Okay? So you can do this, and you can also, right? So orthogonality has the same definition. Okay, so the formula here, the decomposition formula also works. Also works given a basis of eigenvectors, an orthogonal basis. Not of eigenvectors, but just an orthogonal basis. Right? Okay. Maybe I'll explain that in a bit. But right now, I want to give you now the definition that I wanted to get to. Okay? So, yeah, okay, so we have time. Okay, so now I'm going to tell you what an inner product is in general. Okay? So, inner products. Okay? So, definition, right? So let V be a vector space, possibly infinite dimensional. meaning that there's no finite basis. So let's say a real vector space. So it'll have scalar multiplication with reals. And there's a version for the complex numbers. We'll get to that later. So an inner product on V is a function, right? It goes from pairs into the real numbers, right? And we denote it, which we denote by this thing, VW. I'm going to omit the hats now, okay? V and W and V, satisfying the following. The following axioms. Okay. So we want this to be exactly like, we want these inner products to be exactly like, can you guys see if I write down here? All right, so we want it to be like the dot product, okay? So the first thing is that, so we're going to have, it's commutative, right? So for all V and W and V, VW is equal to WV. And the thing that you should think about is functions in the integral that I wrote down. So that's the example. That's one of the examples. That's kind of the new example that we're going to do in this class. All right. The second thing is it's going to be linear or bilinear. So the linearity says for all VW in V and all C in the reals, CV plus W. Let's see, all VW, I need another letter. U in V and all C in here, U. So this thing is going to be equal to C VU plus WU. Okay, and then the third thing is it's what's called positive definite. Okay, it says two things. One is that for all U in V, this product here is greater than or equal to 0. And the other thing is that if UU is equal to 0, then U is equal to 0. It's the 0 element of the vector space. Okay? Okay, so this is what an inner product is. All right, I'll let you guys. So this is in the book too. Okay? So these axioms are written down in the book. Okay? Let me give you a sequence of definitions now. And then we will do examples. Okay, so this is an inner product space. And we're going to use, okay, so let me give you some definitions. Okay, and we're going to generalize these concepts from, let's say the main example are things like this, is like V. You could do things like C infinity of 0, 1 into the real numbers. And then the inner product, say 0 to 1. You could do something like this. Okay? So this is an example of an inner product on this vector space. Okay. So definitions. Okay, so I need to define what it means for things to be. So, okay, let me just give you something. So an inner product space is a vector space with an inner product. Okay, let me give you another definition. If V is an inner product space, and V is an element of V, then this thing here, this is the square root of V with itself, the inner product here. This is called the norm. So this is called the norm of V. Or sometimes people call that the absolute value. Right? So now we have a notion of length, right? So this defines the norm of something. So now we can talk about lengths of functions. All right. Finally, so two functions are orthogonal. So let V be an inner product space. We say V and W and V are orthogonal if their inner product is 0. Okay? So let me give one quick example, and then I'll tell you a fact. So if V, and then we'll do more examples next time, is this thing into the real numbers with, here being this. Let's do -1 to 1, -1 to 1. -1 to 1 of f of x, g of x, dx. Then these functions, then f of x, let's say h1 of x is equal to x, and h2 of x is equal to x squared are orthogonal. Okay, and then we can check this. So let's just check this real quick. And I'll state one fact after this. And we'll be done for the day. Right? So let's check this. So how do we check this? So we'll take the inner product of x and x squared, right? And this is this integral, x times x squared dx. And this is the integral from -1 to 1 of x cubed dx. All right. This thing, well, this is an odd function, right? Right, so this thing is equal to 0, right? Because it goes through, right, you're doing this, right? And this is a negative area, and that's a positive area, so that gives you 0. So those two functions are orthogonal, right? It'll turn out, so the fact that I want to tell you is that, so the fact I want to explain further is that these functions so these are an orthogonal basis. For a certain inner product space. I mean, this is true, but we're going to use this to generalize that formula. So we had that formula where we could decompose a vector into its orthogonal pieces, and we're going to generalize that for this particular basis, right? And so this is what Fourier series and all this stuff is about, and eigenfunction expansion is about expanding in terms of these orthogonal functions. So all those things for different n's will be orthogonal, okay? Let me just say on this interval 0, 1. And this is important. The interval is very important. Okay, so I'll continue with this next time. All right.